In this lecture, we are going to talk about inductor transient circuits. That means what happens in electric circuits that contain inductors when inductors oppose the changes to current in the circuit. Let us first try to understand what happens in a simple circuit that contains an inductor. In the circuit given to you here has an inductor connected in series with a resistor, and this network connected across a battery. The resistor here represent all the resistances in the circuit. Resistances can come from actual resistors, or it can come from the resistances in the wires, or it can come from the internal resistance of the battery, etc. And all such resistances are represented by the resistor R. Ideally, inductor does not have a resistance. So it is just a wire, but that wire is wound into the form of a coil. So when we first turn on the circuit by closing the switch, as we see here, the battery only sees an external resistance because the inductor is just a wire with no resistance. So the battery will start sending a current according to the Ohm's law. I equals to battery potential difference divided by R. However, when this current passes through the inductor, because there is only one loop, the current has to pass through the inductor, and the inductor produces a magnetic field. That is what the coils do. When the current is passing, the magnetic field is coming, and that magnetic field produces electric flux for the inductor. And that flux was not there before. Just a moment ago, no flux. Now there is flux. So there is a change to the flux, and we know from the Faraday's law, the inductor will oppose the change and produce an induced voltage to cancel the change. So inductor will induce a voltage to cancel the current that is passing through the inductor. So the current completely stopped by the inductor just after turning the switch. However, the battery has energy, and therefore battery keep working against the inductor so to send current out. Inductor will oppose. At the very beginning there's a big opposition because it was changing from 0 to something. And now when the battery keep pushing electric charges to run through the inductor's resistance become weaker and weaker, and that means the current through the inductor become larger and larger. So eventually the current in the circuit becomes stable, and at that point inductor has completely given up resisting. When that situation has reached, current through the circuit is stable, and that current has the form of the Ohm's law. That means I equals to battery potential difference divided by the resistance. So when up to that point the current is changing, and this can be modeled by the equation you see here. Let us discuss about this equation a little bit. So we understand that in a inductor resistor circuit, it takes time for the current to become stable. At the beginning, inductor completely stopped the current sent by the battery, and little by little this current increases because the opposition from the inductor decreases, and after some time the inductor stop resisting and the current in the circuit becomes stable. And this can be modeled using the equation we see here. I at any given time equals to the battery potential difference divided by R times 1 minus e to the minus r over L times t. You can see that if the exponential term is 0, then the current is coming as Ohm's law, a battery potential difference divided by R. And that can happen only when t goes to infinity. You can see that when t goes to infinity in the exponential term, it is 1 over e to the r over L, and that is 0. When t goes to infinity, current is battery potential difference divided by R. But at t equals 0, exponential term is 1. E to the 0 is 1, and therefore the current is 0. In between, the current increases smoothly from 0 to the E over R. And therefore, the final current is E over R. That happens after a long time. That is what we call t goes to infinity. And also in the expression, the exponential term has uh, the time. There is t, and but the exponential term cannot have dimensions, and therefore the dimensions of time has to be cancelled by the other term in the exponent. So other terms are L over R. So we claim that L over R has the dimensions of time. So we call it the time constant. So incorporating time constant tau and the final current IF, we can write the current expression as I at any given time equals to I final times 1 minus e to the t over tau. Here we are trying to derive an expression for the energy stored in an inductor, and that is the potential energy stored in the magnetic field inside the inductor. We know when a battery is connected to a circuit, battery will start driving a current through that circuit. And if there's an inductor in that circuit, inductor will oppose this current, and then the battery will have to work against the inductor. Battery can do that because battery is the source of energy. When the battery is working, it has to work against the opposition from the inductor that is the opposition created by the induced voltage. So the work done by the battery during a time dt, while it is trying to pass a current I through the inductor, equals to induced EMF across the inductor times I times dt. This relationship came from energy equals to power times time. So power is potential difference times I, that is the E induced times I term, and we are multiplying it by dt, the time for this process. But we have E induced for the inductor equals to inductance times di over dt. So we can substitute for E induced using this expression. When we do that, the work done during a time dt equals to L di over dt I dt. That simplifies as dw equals to Li di. Now we can get the total work done as the sum of all the little work. That is an integration of dw. When you do the integration, it comes as work done equals to L integral I di from 0 current to the final current. And when you do that integration, it comes as half Li squared. And that is the amount of work done by the battery, and therefore that is the potential energy stored in the inductor. Let us apply this idea into an exercise. Here we have an inductor that stores 0.023 joules, and the inductance is 45 millihenry. The exercise wants us to find the current through the inductor. So that is straightforward. We are going to use the potential energy in the inductor equals to half Li squared. We know everything except the current. We can do this. Here we are going to discuss what would the inductor do when we remove it from the battery after being connected with the battery for a long time. We discussed earlier that when the inductor was first connected to the battery, it will oppose the action of the battery. But little by little this opposition decreases and the current in the circuit stabilizes. And when the steady state had reached, inductor has become happy with the current running through it. So it has a constant magnetic flux. But if we remove the inductor from the battery, that means we remove the switch from the battery and connect it through the resistor and back to the inductor. So now the battery is not there, and then the current sent by the battery is no more. And when that current stops, the magnetic field dies out. And when the magnetic field dies out, the flux in the inductor is going to be zero. But this change is not something inductor will like. So inductor is going to oppose this change and re-establish the initial situation. So inductor will induce voltage to re-establish the current the battery was passing. And that is the first thing happens when we remove the inductor from the battery. However, the inductor does not have an unlimited supply of energy. So the energy stored by the battery in the inductor while it was connected is used to do this work, but since that energy is decreasing, little by little the opposition from the inductor decreases, and eventually the current produced by the inductor will decrease to zero. And that can be modeled by the expression that we see here. I at any given time equals to the potential difference from the battery divided by the resistance times e to the minus R over L times t. And when t goes to 0, exponential term goes to 1, and therefore initial current is battery potential difference divided by R. We know that is true because that is the final current just before the removing the battery, and the inductor re-established that current, and little by little this current decreases, and after a long time, means t goes to infinity, exponential term becomes 0. Then the current in the circuit is 0. So we can use this equation to find the current after removing it from the battery. Let us use this exercise to apply our understanding about inductors. Here we have an inductor in series with a resistor, and these two items are connected across a battery. And the exercise says the switch has been open for a very long time. That means there is no energy left in the inductor. And then we close the switch. The exercise wants us to find the potential difference across the resistor just after the switch was closed. We know that when the switch is closed, the battery will start sending a current through the external circuit. The external circuit has only one loop, and therefore the current sent by the battery has to pass through the resistor and also the inductor. And when the current passes through the inductor will produce a magnetic field, and then the inductor will have a magnetic flux. And that magnetic flux was not there before, so inductor says, no, I don't want this. So inductor induces a voltage to completely cancel the new current, so that it can go back to the zero flux condition. When inductor does that, the current through the loop stops. And when the current through the loop stops, there will be no current passing through the resistance either. And when there is no current passing through the resistor, it cannot have a potential difference, because for a resistor to have a potential difference, it has to have a current passing through that comes from the Ohm's law, and then the resistor will have zero potential difference. So the interesting point is we can see that when just after connecting to the battery, inductor becomes an open switch. So the circuit breaks right there, and that is like inductor becoming an open switch. In this exercise, we have a series LR circuit. That means an inductor is in series with a resistor, and that combination connected across a battery. Exercise wants us to find the amount of energy stored in the inductor when the circuit has reached the steady state. The energy stored in an inductor equals to half Li squared. L is the inductance and I is the current passing through the inductor. And at the steady state, inductor does not oppose what the battery is doing. That means inductor has reduced to being a wire of zero resistance. When the inductor is a wire, the current in the circuit is directly coming from the Ohm's law. That is, current equals to battery potential difference divided by the resistance, which is 25 ohms in this case. And from that we can find the current, and we can use the current in the energy equation to get the energy stored in the inductor. Here we have a multi-loop circuit, and in this exercise we get the information about the resistances and the potential difference and the value of the inductance. We have all this information, and it says the switch has been closed for a long time. Switch has been closed for a long time, and the first thing the exercise wants us to find is the battery current at that time. So the switch has been closed for a long time means inductor has reduced to being a wire. When the inductor has reduced to being a wire, the current coming from the battery sees two conducting path. One is that inductor that had become a wire, and the other is the resistance R1. Resistance R1 has some finite resistance, but the inductor provides completely no opposition. So the current that comes through resistor R2 will not go through R1. Instead, it will choose to go completely through the inductor. When that happens, we can remove the resistor R2 from the network, and then after a long time the circuit reduces into the resistor R2 and the inductor is just a wire. So the current through the battery at this instant is battery potential difference divided by the resistance R2, and the current in the inductor is the same current, and the current through the other resistor is zero because it does not conduct. This part is an extension to the previous exercise. Here we are supposed to find the initial voltage across the inductor when the switch S is open. So we open the switch after being closed for a long time, and when we open the switch, the battery is not a part of the circuit, so we can take the battery away, and now the battery is not sending a current through the inductor, and therefore the magnetic field in the inductor stops, and the magnetic flux is going to be zero, and the inductor do not like it. So it induces a voltage to reproduce the current the battery was sending, and that current is now going to go through the loop created by the inductor and the resistance R1. and in this circuit the current is going to be the same final current in the previous part, because inductor tries to produce the same situation, and therefore the initial current produced by the inductor is the same final current the circuit was running at the end. So the I final equals to battery potential difference divided by R2 is now running through the resistor R1 and the inductor. And in this circuit, inductor is connected parallel to the resistor, and therefore the potential difference across the inductor equals to the potential difference across R1. So we can use Ohm's law to find the potential difference across R1 using the I final current. That potential difference is going to be the potential difference across the inductor, because they are connected parallel. So we have answers. So to summarize the action of an inductor at different situations, we can say the following. Just after connecting to a power supply, an inductor opposes what the power supply does. So it acts like an open switch, so no current could pass through it. Next, a long time after, inductor has become used to the power supply, and therefore it does not provide an opposition. That is, inductor becoming a wire with a zero resistance, so no potential difference across the inductor. And then we open the switch again or disconnect the inductor from the battery. That is after being connected for a long time. Then inductor tries to reproduce what the battery was doing. That is, inductor becoming a battery. So inductor becoming the battery, and it will try to produce what the battery was doing. And then finally you keep the inductor in that position for a long time. The energy in the inductor is dissipated, and it will become a wire. So this wire is not conducting any current, and therefore there's no potential difference. It is an idle wire. We are going to see a very interesting phenomena when we have an inductor and a capacitor connected parallel. First, we have to give one of these devices energy. So that is why we have a battery in the circuit. So we first connect either the inductor or the capacitor to the battery and energize it. Let's take the approach of charging the capacitor first. So let's turn the switch to the left and connect the capacitor across the battery. Then the capacitor will get charge from the battery and will reach the fully charged situation. When the capacitor is fully charged, we turn the switch to the right and connect the capacitor to the inductor. And at the beginning, inductor is just a wire with no resistance. So the charge in the capacitor sees that there is a circuit path for them to discharge. So the positive charges in the positive plate will run through the inductor to meet the negative charges at the negative plate. When these current charges are passing, that is an electric current, and that electric current will create a magnetic field inside the inductor, and that magnetic field will produce magnetic flux for the inductor, which the inductor did not have. So inductor opposes this change and induces a voltage to send the current back to the capacitor. So the capacitor drives electric charges through the inductor, and inductor pushes it back. And when the charges are back, it again tries to discharge through the inductor, and the inductor again sends them back. So we are going to see a back and forth motion of electric charges, or the current in the circuit is going to oscillate. The frequency of oscillation for a given circuit comes as 1 over 2 pi times square root of L times C. So that is the frequency of oscillation in the circuit. We can see that once we energize one of the devices, either the capacitor or the inductor, that energy is going to be conserved in the circuit. That is by assuming there are no resistances in the circuit, so there's no dissipation of energy. If there is resistance, energy will be dissipated. If there's no resistance, the energy given to the capacitor or the inductor at the beginning is going to stay in this circuit. So at any given time, the energy stored in the capacitor plus the energy stored in the inductor equals to the total energy given to the system at the beginning. So if the capacitor has reached the maximum energy, that means inductor has to go with the zero energy, because inductor capacitor gets the maximum energy the inductor was having, so now the inductor has zero energy. At that point, the maximum energy in the capacitor is the total energy in the system. On the other hand, if the inductor has the maximum energy, then the energy in the capacitor will be zero, and at that point the maximum energy in the inductor will be the total energy in the system. So maximum energy will be given to the capacitor at one point, and then the capacitor get fully charged, and then that energy passes to the inductor, and then inductor passes that energy back to the capacitor. So this process is going on. We can use the energy for inductor and energy for capacitor expressions to solve problems using that comes under this category. We can directly apply the result that we obtained for an LC oscillator in this exercise. The exercise says we have a LC circuit that oscillates with a 750 Hz frequency, and the capacitance value is given, and we are supposed to find the inductance. So we can directly use the frequency equals to 1 over 2 pi square root of L times C. Using the capacitor value and the frequency, we can find the value of the inductance. It comes as 2.05 microhenries. This is another LC oscillator problem. We have an inductor with 2.5 millihenry inductance and a capacitor with 7.5 nanofarad capacitance. And the exercise says at t equals to 0, the current is 45 milliamperes and the charge in the capacitor is 0. If the charge in the capacitor is 0, then the capacitor cannot have any amount of energy. So capacitor has 0 energy, and that means the total energy of the system must be with the inductor. So inductor has the total amount of energy or the maximum energy while it is running 45 milliampere current. So that is the clue. Inductor is running a 45 milliampere current, and it is then has the total amount of energy of the system. And the exercise says next, after some time later, the current is 0. If the current is 0, inductor cannot have any energy. Then the total energy the inductor was keeping must have been given to the capacitor. So the amount of energy the inductor was keeping is now equal to the total energy in the capacitor. So we can say that maximum energy in the capacitor equals to the maximum energy in the inductor, and write two expressions. Use the energy expression for inductor and the capacitor to write an equation, and from that equation we can get the charge in the capacitor at that moment. And using the information that is given, we can come to the answer. In the next lecture, we are going to talk about AC circuits.